Okay, we have the pleasure to have Emmanuel Bertin. Emmanuel Bertin is quite famous, especially in cosmology. He got his PhD in '96, then he went for postdoc in Leiden, then at ESO. Then he got a permanent position in France at IAP, Institut d'Astrophysics de Paris, where he stayed for more than 20 years. And then he got a position in Hawaii at the CFHT, where he stayed 2 years. And finally, he found even a better position, in a better place, the Plateau de Saclay, close to Paris. Beautiful weather, much nicer than Hawaii. And he's there since 1 year. And one thing, most of the people in cosmology know Emmanuel Bertin because of his software called Sextractor, which has been used by more or less all surveys in astrophysics to detect sources in images. And I remember the first time I used this software, I was really impressed because at that time we were using a heavy package called Midas. It was an ISO package, and it was just a nightmare to get the sources in an image. And if you had a big image, and it was taking forever. And then when I used Sextractor, just like that, I got all the sources. It was just wow. And that's what Emmanuel Bertin did. So he has a huge experience in writing very efficient software. And so he's going to present us today his most recent work.
Thank you, Jean-Luc. Thank you for coming. Thank you for inviting me. So I'm not really an astronomer. I'm not also really as data scientist. I'm somewhere in between, and also I write a lot of code. So what my main interest is really in challenges in technical challenges in terms of data processing in the astronomical world. So today I'm going to talk about the transient sky, transient astronomy, and what I call next generation skywatching, which is how we can integrate, how we can do wide field imaging using a different way, of doing wide field imaging using video imaging of the deep sky, and also using deep learning to manage to process those video images. So it's very simple. So I will put a bit of context while we're doing that. What are the advantages of doing these things this way? Then I will say a few things about time domain astronomy. And then I will focus on two applications which we have been working on recently, which is detection of transient, adaptive detection of transient, and also how steps towards wide field video imaging, and for instance, and also including a correction of atmospheric turbulence in wide field video imaging. And then there will be many things to discuss in the conclusions, as you will see. So, sorry for the title. I was not able to remove, but it's written Science from Wide Field Imaging. So many of you, or maybe most of you, are involved with wide field imaging at some point in your research. So this is just an example of what we can do with wide field imaging. Jean-Luc talked about cosmology. Here we have an example of weak lensing, that is the shear, which is imprinted on the background images by foreground structures here. So when you have a mass contrast on the foreground, it distorts the images. And so to study this, to map the field, you need a wide field of view. You need to cover this wide field of view, excellent image quality. That is a typical application. So remember, image quality is really important here. We have also mapping of baryon acoustic oscillations. So it's a terrible image, but that's generally how we show things. So we have this preferred distance between objects, between sources that we detect between galaxies on the sky. And so they give us very important clue on the cosmological parameters. So here we need really to cover wide areas, great depth, and also we need, so it's very important to really master the level of biases. We really to be careful about the tiny biases that we may have in the measurement, for instance, of the photometry. Other applications now getting closer to us in the galaxy, we have all the interstellar medium that, well, now we can do this even at high galactic latitude. We can map cirrus, the distribution of interstellar medium in the form of spent cirrus that we see in images now in wide field surveys, deep field survey. We see those huge clouds popping up in images, even at very high galactic latitude, and they are also a nuisance when you try to do also very subtle statistics on the galaxy distribution. So this is another use of wide field imaging. We have also the detection of small galaxy, tiny galaxy, very low mass galaxies, which are just up to down to a few tens of stars sometimes around our galaxy. So we map those dwarf galaxies. So the way we do that, we use a match filter in color magnitude diagram, and we are able like this to possibly detect small halos of dark matter, what we believe are small halos of dark matter around our galaxies. For this, we know how to survey a lot of sky, also to good image quality. And also we have all the other techniques for everything about stellar population. So in this example here, we mapped in this sky region, a large scale region, free floating planets that we discovered by doing astrometry over 2 decades almost of imaging. And so we're able to detect objects at a very faint mass limit. And so why I put this is that many of these applications actually you don't necessarily need, that's very important to have access to observing time, to large telescope. You can be an armchair astronomer, just download data from large databases. For instance, you have the CEA, which covers all the data from the MegaCam instrument since 2004. And so you have at your disposal hundreds of square degrees over several epochs, and it's an incredible treasure trove for science. So this is mainly what we have been using for this project. So this is, I would say, it's not the static part, because as we saw, there was the question of proper motions that we use to find those faint objects. But nowadays, a very important aspect of this of the astronomy we're doing with wide field is transient astronomy for the detection or follow-up of transient sources. So it can go from solar system bodies, here objects. We have microlensing events. So we have also novae, GRBs with tidal disruption events. Also events related more generally to generate gravitational waves. So we're looking for counterparts in the visible domain. So these events, they range in time scales from seconds to weeks or even months. And so this is a very important component now of wide field astronomy, to follow up astronomy. So so what happens is that we have objects which are detected, as you know, in X-ray or the gamma rays, or using gravitational waves. And the important aspect here is to be able, we have fairly large error boxes in many cases, and we need very quickly to find where these objects are. We're looking for the afterglow in the optical or near infrared. And so there are several surveys going on now. Some of them, you know, like this Grand Map project, which is coordinated mostly in France, where we have several telescopes, several small telescopes which are put to work to over the world to be able to follow these events when they happen. It's important to cover the whole world, because this may happen at any time, and it depends on the latitude. Of course, you may be able to observe it. Sometimes the weather is good, sometimes the weather is bad. So it's compared to, for instance, other types of wide field image projects. Here, the important thing is that you don't have necessarily an observing plan, you know, well defined, when we say, okay, we will cover the sky like this. We will map the sky in such a way that you know, we observe with given image quality. You have criteria for image quality and so on. Here, when it happens, you have to observe. It's sometimes in not very great conditions, and you have to make sure that you detect something that pops up in the image, that appears in the image. So what I will discuss now is really observation, wide field astronomy in this context, which is a bit special. Hi. So let's start really from the beginning. So taking, almost from the source sex factor, the basic way, of detecting objects in astronomical image is known as the match filter. It's been around since the 40s. So you can derive an optimal linear filter in the least square sense if you want to detect specific objects for which the profile on the images, and it's known as the match filter. So in Fourier space, this is the expression. And so if you want to, you can show very easily that you can get an optimal form for this filter, which for white noise, if you have background noise which is white, it's equivalent to a correlation with the profile of your object, the point spread function, if you're looking for point sources. If you're in a crowded field, so you are limited, but it's called convolution noise, and in that case, this formula is equivalent to having some kind of deconvolution. And here's an example here of, it's just a simulated example I use for teaching, which is I put some CMB power spectrum here on top some point sources, and you can derive the optimal filter, so linear filter, which looks like that, and then it's very easy to threshold, and you get something which is much easier to detect point sources. So why I'm going back to the basics is that from there, you see that with a correlation filter, it's better to put a correlation filter on a convolutive filter or convolution filter, because in terms of, it's meant to really to correlate things to find where things are. We can build on this concept and extend it to make it more adaptive. Here, it's constant in this area. So very early on, many years ago, people have tried to improve that by moving, more to something a bit more intelligent, by doing something that you can train, a system that you can train based on the data itself. So there were two efforts at that time, at least. One which we called I, which we used at the time to filter out the images to enhance through machine learning some patterns. Here in that case, cosmic ray impacts. We wanted to get a map of cosmic rays and to separate them from regular objects. So it's very, it's early times. So you can see actually it was a very simple convolutional neural network, but it had no name at that time, but it was like this. There was another effort by Andrew et al. in 2000, where they put an extra layer with a PCA. It was an extra layer. So it was used in production, but as you can imagine, there was not, basically it was an adaptive convolution filter, because there were some non-linear components here. Everyone is familiar with convolutional neural network? Okay. So then, more recently, as you know, there have been deep learning with convolutional layers. So the breakthrough in the 2012 or a bit after was really, actually it comes from earlier than that, from Bertin, but really thanks to GPUs and also to the ability of large training set, people started to use neural networks that use convolutional layers, where you train actually the system to adapt the convolution kernel to perform some process. Generally, in the end, you have classification, but you can have also regression. And this system was extremely efficient, as you know, and it was the start, I think, of the last revolution, I would say, of AI. And so it's been used a lot now in astronomy. Maybe not so much in regular software that you can download. It's generally people derive their own systems, and so so you need GPUs generally to do that. So you can see this review, nice review 2023 for a complete server application that include a lot of convolutional neural network. So here, as you can see, using convolutional neural network, we can extend the concept of this match filter for detection now with something adaptive. We still have convolution. We will still have some kind of thresholding in the end, which is done because of the thanks to the nonlinear function. so the name escapes me, so the activation function, yes, sorry. And so it comes naturally after training. And of course, there are some subtleties I will talk about. Now there are more sophisticated neural network, vision, transformer, SWIN, and so on. But for this talk, I will focus on this because, I mean, even with such a simple system, we can already do a lot of things. And the interesting part is not really in the architecture itself. Of course, we can improve on it, but on the way you're using it and quantitatively how you're using it. So the first thing I'm going to talk about briefly, if I have enough time, is a project we have been doing at CFHT last year, which is Olino. It means glittering in Hawaiian. So that's why I showed this image of the sea in Hawaii. Which is the idea here, as I will explain, is to have an automated blink comparator. It's not new. People have already done that for several years, but here there is an extra thing. So here I'm just showing how a blink comparator, the principle of the blink comparator. You have two images taken at different times, and something happens in the sky. An object moves, an object appears. And until almost the 80s, the 1980s, people would use this kind of specific microscope. It's not binocular, but it was a kind of microscope where you have a mirror that you can flip and you move from one image to another. And by moving it quickly, you can do that with DS9 and virtually. You can see, oh, something happens here. Or sometimes you can use a binocular and then you use the stereoscopy to detect things. It was quite basic, but people discovered a lot of things like Luyten, for instance, to discover nearby stars because they move fast on the background sky. So here we are interested by the detection of transients. So it's written differential image photometry. So really the golden method to do that since the late 90s, early 2000 has been you get two images at different times, one which you call the reference image, another one which is, the other image, the science image. You register them so that they match on the sky, and you try to compute a convolution kernel that would allow, by convolving one of the images, that will match the other image. So it doesn't have necessarily to be the good image with the sharp image that you degrade to go to the bad image. I mean, you have some margin here, but the idea is that you do that, you find this kernel, so there are a lot of regularization or implicit regularization sometimes going on. And in the end, when you subtract them, you see what has changed. So it's very useful in crowded fields because you cannot just do a comparison of catalogs because of the blending and so on. This is where deep learning gets in the process. So since the end of the 2010s, basically, people have tried to put some deep learning in them, convolutional neural network. First, to try, I mean, one of the difficulties in this method, it looks simple, but it makes the implicit assumption that, for example, that the Nyquist criterion is met everywhere. And there are lots of junk on images. You cannot imagine how much junk you get on one field imaging. I mean, it's okay if you service 1,000 pixels, but when you start putting in billions of pixels, of course, things happen, bad things happen. And you have all the artifacts, you have a lot of satellite tracks now, you have cosmic rays, you have strange things that, I mean, you never know really what happened there, but you also have sometimes some strange turbulence, I would say some kind of rogue turbulence happening. So you need some vetting in the end, because otherwise, if you do that and run, for instance, a source extraction software on this, you will end up with a lot of events. So in order to get something, I mean, if you don't want to be to have a lot of false positive, to be buried under a sea of false positive, you really need to have some intelligent vetting which is done. So this is what people have done first. That is, very simple application of CNNs using training, generally using students that painstakingly, classify good events, wrong events, and then you train the system and it works. But it's still complicated because you still have to go through once again, the painful aspects of this processing, which is you have to align very carefully the images. You have to make sure that everything is perfect. Where you have to mask out everything that doesn't follow basically the decrease criterion, or otherwise you have aliasing artifacts that generate events. So it's, in practice, I mean, it's simple on paper, but in practice, you have to spend years to develop software to do that. So, well, recently there have been efforts to make things, you know, to directly to do the process intelligently using a neural network, convolutional neural network that will do these things in a way that it can filter out most artifacts. So it's not simple convolution, subtraction. It does the process, but also it manages the artifact. So this is what things are, how things are being done. And also you can use GPUs to do that. So it's faster because GPUs for convolution, they are made for convolution basically. And so now, so the idea here is to go one step further. So this is work that has been done mainly by Vincent Deloupi when he was at CFHT. He's now in Antarctica, so doing something else. So we are currently completing a paper about this, which I will describe right now. So the idea is to go one step further, is that we call it a one-shot transient detector, because you only need one image. So the trick is that, of course, you don't have the reference image, you don't have your reference image. You can use a reference image from a pre-existing survey, which has not been taken by the same telescope. So it's something like you would do, you know, like an expert would look at those images. Okay, this PSF is bad here, we know where are these effects. But it looks like, you know, it's maybe a real event. Kind of, we are entering a fuzzy area here. But as you will see, we can manage anyway this kind of process. So the idea is that you pick up your survey. If you have the northern hemisphere, I mean, you have this Pan-STAR survey, which has been done in on Maui and in Hawaii, which covers 3/4 of the sky, all the northern hemisphere, plus a bit of the southern hemisphere. And so if you have a telescope operating in the northern hemisphere, like here, for instance, everything you will be imaging basically has already been observed by this telescope to the depth, typically to 23rd magnitude, which is already good. If you have a small telescope, you don't expect to do a transient survey much deeper than that. So how did we proceed? So here's the architecture that we ended up with. Very simple CNN, convolutional neural network. So we start with images. So we actually scan the images. So we have a scanning process, very simple with some overlap. We tie the sky and we end up, it's very simple, with a single output, which is a classifier, which we would like to be ideally a posterior probability to have a real event, at least a detectable real event in this particular piece of sky. What makes things more complicated here is that compared to a simple system is that we have to deal with image depth, which is different for both image samples, one from your telescope, one from that you pick up, that you download for a database, from a database when you observe. And also you have those PSF that change with time, that are different for both images. This is why we have this extra branch here. So this extra branch has the two PSFs normalized, which are provided to the neural network and down to the, so it's a convolutional stages that we have here that end up in the same fully convolutional part here. And on this other branch, we have the data, the two data, because they're on the same grid. And we have also what we call weight maps, so maps of bad pixels for both images, one for your own telescope, imaging, for example, you have a back column, so it's nice to indicate it. And this one's also for the reference survey. So just to show you an example on how bad things can be, so that's why it's quite challenging. Here is an example of, I mean, it was at CFHT that we did that. So we did that, of course, with megacam images, which is the wide field imager, optical imager at CFHT. And so here in the video, you see the same region of sky observed with megacam. No, it's real-time processing. So we have the flat fields from a previous run, so it's fairly dirty. But we don't care. We have deep learning that takes care of this. And then we have the corresponding part of the sky with Pan-STARRS. We see Pan-STARRS one survey is pretty ugly in terms, you know, it's stacked data, lots of junk, noise is not really stationary. And So the way we work, of course, is that we use our own telescope image as a reference, and we map the survey, the reference survey, back on this pixel grid, so that we don't touch at all the new data. Here is an example of the training. How we did the training? So we use augmented data. So what we do is that we take parts of the sky where we don't expect that many transients, so we avoid the ecliptic where you have all these small bodies crossing the images all the time. So we know that we expect typically for given exposure, typical megacam exposure, 1 transient per image. And then of course, we put many more dummy transients using a PSF model that we have for every image. So we have 2 kinds of transients. Small trails, because we want to detect small systems, solar system bodies or things that that are around the Earth, and also regular point sources. We put about an equal proportion of sources that are not detected. Sorry, no events and events. Of course, it's completely wrong in terms of priors because we expect a very low rate of priors, but I will explain how we deal with that later. So we have a mismatch here we have to correct for. And then we have the different PSF. So of course, there is a small pipeline upstream that just, regular pipeline that you have anyway on most telescopes that take your image, maps the astrometry, that gets the astrometric transformation, that maps the PSF model. And so this is just the astrometric distortion that we get on the reference image for that very part of the sky and the megacam here. We do it very roughly. You see, we just use something linear. So it doesn't have to be very accurate because once again, it's part of the training too. And we allow the events to be slightly, wrong in terms of astrometry. And as you can imagine, what will happen is that if you have, for instance, a fast-moving star between the 2 epochs, there will be some kind of threshold where poof, it will be detected as a transient event, or otherwise it will be, of course, detected as a non-event. So now we have to deal with what is called class imbalance. As you can imagine, we train. So provided, if we believe that that our neural network has a sufficient number of free parameters and that our sample is dense enough, actually it's a situation which is almost never met, but we assume that we can do that. As you know, the system with the type of cost we're using cross entropy cost function, you can show that the system will converge in principle to the output will reflect estimates of posterior probabilities to have an object, in that case, in the field or not. That's again, once again, it's in the ideal case, but we have to, we need something to deal with. Of course, this will be using the priors of your training set. That is an almost equal proportion of true events and non-events. Of course, this is very different. Actually, you expect a fraction of true events in 10 to -3. So with this kind of training set, you would have only you could only put one sample in one event in your training set. So of course, what we're doing is that we balance the data sets and then we train it, and then after that we correct the output of the neural network using what's called a prior probability shift, something which is used quite often, and which has several advantages. One is that since we're balancing the samples, actually, when we look at the likelihoods of let's say rather the distribution of in feature space of the events and non-events, because we balance the 2 data sets, we map very accurately the regions where they overlap much better than if we had actually real priors on the different for both classes. So anyway, it works well. So we don't experience a lot of mismatch. So we train with a variety of images which are representative of our instrument and the site where we observe. So in terms of megacam, we have so many images that we can really sample very well let's say the space of image quality. Well, if you don't believe in that, you can still work the usual way. You have the receiver operating characteristic curves, and then you select the threshold that will give you the appropriate false positive rate. Which works very well. One very important aspect is that if you do that, maybe some of you have already played this kind of game. What comes out inevitably is that you will detect events, rare defects, effects that are very rare that no one sees, but well, we are looking at something at the level of 10 to the -5. So incredible, bad luck of things just on top of each other, cosmic ray that, another cosmic ray that really looks like, okay. So there is absolutely, in this kind of training, you need absolutely this extra stage where, when you identify, you look by eye, the remaining false positives, and you reject them in your training set, being labeled as no events. And it works extremely well. It's like, well, some kind of training for dogs or you should not do that. And so you do that basically 3 times, you iterate 3 times, and in the end, you get a system which is really reliable for a given instrument. And to such a level, these are operating characteristics that we get. So they just give you the level of true positive rate as a function of false positive rate. Note that we have to use a logarithmic scale on the false positive rate, because otherwise, in linear representation that people use very often, you will get something like that. So we get AUC, so you see at 99. I mean, especially when you look at the images which are really completely different. And here I show the different rod curves that you get depending on the magnitude limit that you fix. So basically, we see that we reach the magnitude limit actually, which is limited by the pan-star surveillance example in this case, which is around 23rd magnitude, as you can see. This is for 3 filters on which. So the Alban filter is the worst one because Megacam does not work so well in the Alban filter. But still, I mean, it's perfectly usable because except for the very last magnitude bin, you see that we already have 80% completeness for the given target false positive rate. Yeah. Okay. So just to conclude this part, we believe we have robust detection even without data. Works well for every event which is at, let's say, at Q sigmas. It's great for sky surveillance. You have a system you can plug on a telescope. It works almost in real time. You take you have your pastor either locally, but it's large, or you just download. This is what we're doing at CFHT, and you get a system that gives you probability. If you want to see how it works, you can go just there. You can do it from your phone. It works well on a touch device. I just show you an example of a random images that we use. And you can compare with that. You can see that basically we detect all the known asteroids for the very exposures. Okay, there is one point which doesn't work perfectly well, and which is annoying for the science aspect, is that we are not working so great for events happening on galaxies, which are the interesting ones, the GRPs and so on, or supernovae even. And this is what we're working on right now. We're expanding the data set with putting stronger priors so that we make sure that we have a large fraction of the sources and the training set that are around galaxies and that match more or less the distribution that in terms of magnitude and position that you expect from supernovae, for instance. So this is going on right now. So we already have encouraging results. So this is great for sky surveillance for small bodies on the sky, but not so great. We're basically beyond 19th magnitude. We're not doing so well on supernovae. But the final product, should I say, will handle that very well. Okay, now let's move to another aspect which I already described during the Titan meeting, which is now we go one step further. We're not only interested in regular exposure of the sky, but we want to go one step further by moving to video imaging. Currently when we are doing wide field imaging, we are doing long exposures, like very often in astronomy, at least several seconds. We're doing that for several reasons. The main reason is that we are dealing with detectors for which, just acquiring the images, there is instrumental noise on top of photon noise on top of it. So if you have not enough photons, this instrumental noise dominates. Hopefully now there is a new generation of detector, well, not so new, but which has spread now a lot, which you place on your phones, because your phones have small aperture, small pixels, so they don't get many photons. So people are really worked hard in the industry to reduce this instrumental noise, which will read out noise, and we can use them in astronomy. Amateurs use them a lot, but professionals not that much. They're very, very interesting for time domain astronomy. Yeah. Okay, so what are the advantages? What would be the advantages of moving from traditional long exposures to oh, I know what, sorry, something went wrong here. Yep, anyway, it should be, sorry, let me check maybe, yeah, no, sorry, it's the next slide. So, first of all, with current wide field imagers, even, for instance, an SST camera, there is a non-negligible time that is used just to read your detector. And if you, for instance, if you want to cover very quickly the sky with a large instrument, it's not negligible at all. It's never done less than 2 seconds, basically. If you have large detectors for CCDs. And in the case of mega camera, it is 40 seconds. When you look at statistics, it's up typically between 10 and 60% of the available time, which is not so great. Moving to video imaging, you just run a video. There is no shutter action required, no issue with shutters, that break down sometimes. No guiding, because if you're observing sufficiently fast so that you don't have motion blurring from maybe some move of the telescope. Don't need any derotator if you have an multi-azimuthal telescope, so that's saving money and saving problems. Something very important, if you have people, you're doing a survey, you have people interested in using your data for tracking objects that move, you can do digital stacking. That is, you can virtually do non-sidereal tracking. So you can both provide data for people interested in the static sky, like extragalactic people, and also to do some kind of digital stacking or even clever digital stacking that that does all these different positions that do virtual tracking of objects that you want to detect. So this can be done also in real time using GPUs, of course. Another thing which is interesting that you can do real-time monitoring. So you can monitor in real time the photometry in your wide field of view, how things are changing. And as you will see, we can also map the profile of turbulence in the atmosphere. And also we can use the fact that from small telescope, you can use the fact that you have a twinkling of the stars also to get constraints on the turbulence. And of course, you can do Loci imaging. So Loci imaging is, in astronomy, is you take the best exposure, you take many exposure, and you take the ones for which the turbulence is the lowest, the images are the sharpest. But actually, you can go beyond that, as you will see. And you can mitigate the impact of temporal artifacts, like satellite tracks, and the blurring from the atmosphere. Satellite tracks are really an issue right now. This is a real image. It was an astrophysical image of the day a few years ago. So especially at dawn and at dusk, if you're working in observatory with wide-field instrument, you know what I mean. You get those satellite tracks now everywhere. And the reason for this is the number of satellite constellation, the number of objects moving around on the orbit has exploded over the past few years. So you see mainly after in 2020, and it's getting worse and worse every month. And once again, mostly at dusk and dawn, because satellites are still lit by the sun, but there are still issues also later in the night. So, and it's a problem because a lot of people, for instance, tracking solar system body, they work at dusk and dawn. So with video imaging, you don't have this issue because of an object instead, typically a low orbit object goes at a speed, an angular speed of 1 degree per second. So if you image at, let's say, 10 images per second, you have only covers a few minutes, half minutes. Okay. Now we can afford doing video imaging because we have detectors that have a low readout noise. They are called SCMOS detectors, and they are quite different from the CCD we're using generally in astronomy, where we move the charges. I mean, they are still, we're moving the charges from pixel to pixel, so it's kind of analog processing. Then we put them in once again, an analog buffer that also move the charges to amplifier digital analog digital. We have an amplifier for every pixel, and we have, depending on the architecture, we have matrixing, and we have several analog digital converter. So in the end, what happens is that we have a much lower readout noise. This is a simulation I did of the same piece of sky. We're using a recent CCD like you will get on LSST or yeah, a bit, no, it's a noise of an LSST detector typically. And this one with a CMOS camera, what you can buy for $200 in the, you know, in the shop. And you can see the readout noise is almost 10 times lower. So it's a difference when you want to detect objects. So you see the turbulence that you get. This is a simulation, but it's quite accurate. So, and to the point now that in the labs, you have wide field detectors with many pixels where you can actually count the photons. And here's an example. So currently we are at this level for the cheap detectors. So you see, so we are not there yet, but there are already prototypes which allow you to count the individual photons. So you don't care about the exposure time anymore, except in terms of processing. So this is what happens on video imaging. It's a bit slowed down. You see, this is a low orbit satellite that one per second. You see, it's very easy to isolate. You take all this exposure. It's very easy to isolate, you know, to remove a few exposure or just mask out this region. On a long exposure, you would have a big track like that. And the exposure times are very low, 1/10 of a second here. Another example for this time, we have a very distant guy moving. I don't know what it is, but this is what we observed at least last December on the 1 meter C2PU telescope, which has a very large field of view. It's almost like Euclid. It's half a degree on both sides, almost. Okay, now what is interesting is that since we have video imaging, we have video of the sky, we can do more than just filter out things that we don't like. We may be able to also to correct for the blurring of the atmosphere. What happens is that when you observe some sky through the layers of the atmosphere, different layers which are turbulent, so they have refraction indexes that varies. So you end up with a wavefront which is bumpy, and in the end, this is how the point spread, the instantaneous point spread function looks on the telescope. When you zoom a lot, you see all these speckles here. So each speckle has the size basically of the diffraction pattern of your telescope, of your instrument. But it's somehow spread and multiplied by the number of, let's say, turbulence cells that you get on your line of sight. So this is with a very large instrument. This is a 4 meter, I think, of my simulation. If you move to a smaller telescope, you only have basically one main speckle, and simply because your diffraction relative to your to the sets, the diffraction pattern relative to the side of the speckle is comparable. So what you have basically is a wandering point. And typically in the visible, you have with a typical between 50 centimeter and 1 meter telescope, half of the blurring is due to this wandering component, to this moving component. The other is your diffraction spike, is your diffraction pattern, and also combined with a higher order variations that you cannot correct. But you're dominated by the tilt of your wavefront in that case. So you see, it's kind of obvious to remove that. And it has been shown many times since the 70s. The latest paper that dealt with that by Kaiser et al. In 2000, Nick Kaiser, he was interested in getting good recurrencing images. That you can improve basically this is the scale ratio. You can improve your sync by a factor of 2 if you're tracking, you know, all these wandering objects. So it's called fast guiding. Also, it has been used since the 70s. There have been instruments, but mostly for now on small field of view. The challenge is on wide field of view. If you want to do it on wide field of view, these are examples of instruments that do this, that use this. So on a wide field of view, I mean, everyone who has observed the moon in the telescope knows how what happens is that actually these isokinetic regions, they are different. I mean, they are limited and they depend on the altitude of the turbulent layer. The turbulence, which is very close to you, is identical. I mean, for a given line of sight, you get the same pattern on all your field of view. But as you move up in the atmosphere, you get decorrelation at different angular scales. And so here, the component that moves all things together is the component from the ground. And the component, that does like this at smaller scale is higher in the atmosphere. This was taken from my backyard, actually. This is around the Tycho crater. So there was an effort, you may have heard of it, the OTCCDs, orthogonal transfer CDs in 2000. This was the Pan-STARRS project, the original Pan-STARRS project. The idea of Nick Kaiser and Jerry Lupino was to have a detector, a strange type of CCD where you can move charges on both directions. You would use guide stars on the sky to move charges in this, to follow basically the distortion of the atmosphere in order to correct for the images. It didn't work. It worked on paper. They had some samples that were promising, but in the end, these were early days. It was not a CMOS. They had it would generate a lot of readout noise. And they had another issue. It was a wide field telescope with a large obstruction. It is generally what happens when you have a wide field telescope. You have a large obstruction. So your instantaneous PSF, amateur astronomers know that the central peak is strongly shunted, is really reduced, and the more energy ends up in the rings, which is not an issue when you have long exposure because the whole thing fits easily within the seeing spot. But when you want to do things instantaneously, you lose this sharp aspect. This is why astronomers always prefer to have even refractors because they are not obstructed. The images look sharper. They have the sharp aspect because the diffraction PSF, fraction limited PSF has a sharp peak. So too bad. It was really ambitious. It's a nice project. So however, in his 2000 paper, Nick Kaiser, what he did is that in the original project, it was supposed to be a network of small telescopes, because the issue here is that when you're observing a high latitude, so Nick was mostly interested in faint galaxies, of course, at high galactic latitude, you don't have that many guide stars that you can detect instantaneously to guide on. It's larger than the isokinetic region generally. So the trick was to use several telescopes and, basically for a given patch of sky, patch of turbulence, you will always have a line in the statistical computation, you will always have a telescope for which there will be a star in that very patch of turbulence. So I computed that on top of Mauna Kea, with 16 1 meter class telescope, you could map the whole, to more than 95% completeness, the high galactic latitude sky. And the seeing, he was expecting to have a typical seeing of 0.25 arcseconds at Mauna Kea in the near infrared, very near infrared. Now we're more than 20 years later, but we have new hardware at our disposal. So we still have those 1 meter telescope. Remember to use low obstruction if possible, so that you don't you make this peak, you keep this sharp peak. This is the example of telescope we have been using. Just an example here that we did, manually by painstakingly, readjusting the astrometry. This is what I could get from my backyard. This is a CFHT image I could find on the web. You see, it's a bit better, but because for that very nice, Megacam didn't have a very good seeing. So here you get typically 0.8 arcseconds, but this is just from backyard in around Paris. So large camera. Now we have now we have this CMOS camera. You can buy them for a few $100. They are it's very easy. The problem is that for the large ones, you get 1 gigabyte per second typically when you observe. So you have to manage that. That's the main issue. So you need to have stuff that can move your data at 1 gigabyte per second, record it or process it with a fast GPU. That's the challenge. And you need a good forward model because we're going to do machine learning to train this. So the way we have been doing this is to develop a simulation library which is optimized for wide field imaging. There are some turbulence simulation libraries down there, but they are mostly for adaptive optics or tiny field of view. Here we need to cover 1 square degree, for instance. So there are some compromises which are completely different. So we use a typical frozen field approximation. So we assume that the turbulent layers with variation of refraction index that they don't change when they move across the telescope pupil. We work at centimetric resolution typically. We use a Fresnel propagation, so which allows us to have, of course, better accuracy than with Fraunhofer, and also we are able to have twinkling stars in the end. We can map instrument pupil aberrations. Our implementation is in PyTorch 2. I mean, we just use a neural network framework to do, like GPU-assisted NumPy, more or less, and it's extremely fast. We optimize the way it works with FFTs, batch FFT, and tensor folding and unfolding, and we can generate with a video game card 100,000 PSS per second, which is, so you can simulate reasonable field of view almost in real time. It's really impressive. Here is an example of what you get. So we use a von Karman model here with a 0.7 axon seeing in the R band for 1 meter telescope, 30% obstruction. Sorry, the video normally is much smoother than that, but so this over field of view. So we have a grid of stars. So we have more than one speckle here. We have more speckle because we have several fit parameters. The fit parameters may be around 20 centimeters, maybe in this. So we get a bit more than one speckle, but you get the idea. So we are going to use that again with a convolutional neural network, which maps images to images. So we used, a fairly old model, as you know, the UNet, it's called the UNet, very simple model, which we use for regression this time. So we have the degraded images in input. So actually a sequence of images, 64 typically, 32 or 64. So it corresponds to 6 seconds of imaging. And the output, we say, okay, do me a stack of these 64 seconds. We learn to reconstruct a stack which is corrected for astrometric turbulence, for turbulence. So Spencer Balak did that in web paper was released this year. We have a very standard model with a few adjustments. We try to have, of course, stationary noise, so we move to unstrong transform. We have, but basically, otherwise, it's your regular unit, regression unit with a chi-square cost function. So nothing very, it's all in the simulations and how we do it. And now, what do we get? So this is an example now that we get on test data. We have we have a system that adapts with between bad seeing and good seeing. Here's the ground truth of a simulated field. So we use typically Gaia catalog to do that. Here is what we get on the video frames. You don't see much, right? Here is what you would get with simple averaging, like we do actually when we stack generally data. And this is what you get in the inferred data from, and you can see, of course, it's both stable and actually much bigger than here. So our ground truth, we assume that we are limited by diffraction. So this is an interesting case because in this data, also, this is the same thing now, but we've stacked. So we have this series, what you saw were videos, previous one. Now we stack the videos, and this is the result that we get here. And this is interesting. This is an interesting application because, as you saw on the videos, we have these speckles and so on. So we know that the high frequency of the images is there. It's not yet, absorbed. It's not yet averaged out. But of course, it's complex to recover. So the simple way would be, to use some kind of optical flow algorithm where we just move the data, so you can. But this we go one step further because we actually reconstruct the images and we use other information which is more than just the shift in position. Quantitatively, what do we get? On the sample that we get only very limited imaging for this project. We had issues with telescopes and so on. I won't talk about this, but we get, well, modest but still significant improvement in depth, and also, of course, in a crowded field, you get all the better deblending. We are able to preserve the photometry. The astrometry, we don't get any improvement. Of course, we obtain a Strel ratio which is very close to 1, except, of course, at the limiting magnitude here. So the magnitude are quite modest, but remember, we are at video imaging here. The video imaging rates. And of course, the question, does it work on real data? The answer is yes. This is an example that we took there. So previously it was simulation. we are in the vicinity of M92, so we're cheating because it's quite a dense field, and this is what we recover. This is a video, by the way. This is not an image, so you see that it's really stable. And quantitatively, since we have Gaia stars, so this is the way we process for large field of view. We just scan the images. We get more or less what we get on the simulation, except that since our noise, we have correlated noise, which is not so, which gives us a pedestal in terms of noise, so we don't do as well as with the test data, but it's very encouraging anyway. So, yeah, it should be. Okay, so just to conclude for this part, so I believe that high cadence video imaging carries a lot of potential for wide field imaging. Hardware performance of detectors and also of the GPUs is steadily improving. So we have still, don't store those data. We did that and we ended up with a lot of SSDs everywhere. It's a mess. So it's important to process data on site if possible. That is to generate virtual exposures, for instance, every minute. And not try to store these things. It's already been shown in star field in terms of results. Our models are very simple. They are not generative. We don't go to the generative way. So far, there is a bit, of course, of hallucination in there. So we have to investigate this. We clearly need to explore things beyond CNNs to extend angular and temporal reach. More external priors currently, for instance, something we could have done is that we know the Gaia sky in this part of the sky. We could have used Gaia stars, for instance, to give a reference in astrometry, which should have helped normally. We have not done that yet. I mean, there are lots of things to do. We have not managed transient artifacts currently, so we assume that we don't have not managed transient artifacts. We have to put this in the training. Something I will discuss is the possibility to do atmospheric turbulence tomography, and there have been also suggestions to combine with ground layer adaptive optics, which would take care of the high order of the atmospheric distortion, but constant over the field of view, and we will take care with this algorithm of things that happen at a higher altitude. Yep. Okay, just to discuss this idea of, and I will conclude with this, of doing tomography of the turbulence in the atmosphere. What happens is that you have a large field of view, a video, where you have stars that move, right? The stars that move together over a large distance, you know that they correspond to the turbulence that happens at low layers. And as you increase, of course, the altitude of your turbulence, it makes the apparent move of stars decorrelate. So you can see there must be a way to, to taking the video to generate, to infer a distribution of turbulence of the amount of turbulence as a function of the altitude. So this has been tackled by Paul Hickson in 2019. He had other interest, but he did it, the pedestrian way with a statistical model and so on. I showed he had not very great data, so it's really a challenge that he managed to deal with. And he managed so he separated, he had a model where he assumed that the turbulence was in layers. He could not go above 300, he didn't have enough statistics in his data to do that, but he was able in several examples that he shows in his paper to find, for instance, in this case, I just took this case, there are several plots, that there was a major contributory component that would come from a layer at 50 meters above the telescope. But we could expect with a convolutional, not necessarily convolutional, but a neural network that would have an input, a piece of video, and in output, distribution as a function of altitude, a simple vector, to be able to generate something like that almost in real time. So that will be very useful, for instance, for people doing data transmission kind of thing. There are similar things being done right now with using the lunar surface. People are doing that, but of course, they only can point on the moon. They are not using deep learning. Another thing, and I will end also with that, is moving. Once again, we have this problem of, which is not as strong as what Tonry, Lupino, and Kaiser had in 2000, because thanks to deep learning, we can actually track on stars which are not visible in individual exposure. The tracking is not perfect, but we can see really we have examples where we had field where in the video we could not see anything. But in the resulting reconstructed image, we could see the image stabilizing quite well, quite impressively. But still, at high galactic latitude with a 1 meter class telescope, you don't really, you're not able to properly map every part of the sky. There are regions where you don't have any sufficiently bright star in a given area. So there are several solutions. We do so this is our simulator allows you to do that. You can map the same part of the sky from different point of view, with a small parallax. And so you can, once again, you can use that, fetch a neural network with this extra information to do the mapping. But of course, you would need either those 16 telescopes in that case, or you would need to split the pupil of a larger telescope. So there are several ways to split pupils. I don't want to enter in detail. I've looked into that, whether you could use the equivalent of light field camera, where you can separate but then you are very quickly, you hit the Abbe diffraction limit. So another way, which also remains to explore, is just to work only with data, not to try to decompose, to split the pupil, but work with actually images with a lot of speckles. So this is what is called holographic image reconstruction. So here is an example. You have it taken with a large telescope. You image a part of the sky where you see the speckles on these individual frames. And actually, so still the same issue. Actually, you can reconstruct the images very simply. Simple algorithm, just a bit of regularization, you can do that. And you can expect, they do that only with a bunch of exposure which are completely decorrelated in time, but with video rates and with deep learning, one may expect to be able to reconstruct high resolution images, despite the fact that we have several speckles. It's a challenge. We don't know if we can do it, but it would be worth doing it. It would not be as good as your regular adaptive optics, because remember the light is spread over more pixels, so you don't have the same signal to noise. But in terms of definition, it could be competitive. Okay, just to summarize everything, we know that even simple models, if you have the right training set, you already have the ability to tackle wide field imaging problems. So for instance, timed image sequences. So of course, you would expect performance to be limited by angular and temporal reach. So far, we haven't seen the need for some kind of adaptation or transfer learning. If you have a good enough forward model. So this is really the key. And this is where it's nice to be an astronomer, because you know exactly what you put in your simulations. GPUs are mandatory, of course. The nice thing is that you can integrate those simulations in the machine learning framework. I think Jean-Luc, I remember you had a paper also where you did that for PSX, where we have both. So the nice thing is that you don't have to store samples necessarily. You benefit from batch processing, just-in-time compilation of Python code, and so on. So it's quite clear. And so something we have not addressed is that you don't know the uncertainty of the reconstruction, but in principle we can do it. We can sample the posterior distribution. There are several ways to do it. There are even very basic ways like Monte Carlo dropouts, but we try to do that. It's interesting, but it's completely prohibitive in most cases. As usual, it's interesting when you develop such a system to distribute the data sets so that there will be emulation between teams to try to reconstruct prime point images. Something we found out is that visualization is really critical for qualitative assessment of performance. Some things like DS9 do not cut it. That's why we developed our own system. Yeah, and I think that's it. Thank you.
Thanks, Emmanuel. Do you have any question? Yes.
I want to ask, what is the maximum magnitude that you can study with experienced technique?
So typically, people go a bit above 10 kilometers, between 10 and 20 kilometers would be the high. Above that, generally, you know, the atmosphere is too not dense enough so that it does not matter too much. So we get typically, yeah, I would say 15 kilometers would be the higher. I mean, if you would use a discrete number of layers, the higher ones would be maybe at 15. I mean, there are effects above that, but there would be below the 0.1 arc second in terms of. So typically, what people do is that they map, you know, it's not linearly spaced. They have the ground layer, something at maybe 50 meters, 100, 200, you know, it's more logarithmic.
Emmanuel, you mentioned that the technology is more mature now to use this video technique, right? But do you envision that in the future for in small telescopes where we don't have enough, we cannot buy really wide field of view CCD detectors, you could envision a system where you would use a CMOS camera coupled with a GPU and take a video of the sky and just process your data, just forget the old CCDs.
That's
how would you deal, because you also mentioned that we're discussing, how would you deal with the fact that the SCMOS detectors are not as flat, right? How would you deal with, is it only geared towards stellar, wide band? So even if you want to do narrow band filters.
So I have yeah, an answer to that. So we have a paper which came out last year with Marc Betul, who was the first author, where we got QHY CCD, they landed us their higher resolution model, 150, and they have this system at LPNHE in Paris. They have this calibration system that they use for LSST, which was star dice. So we put this camera directly there. Okay, so we derive the quantum efficiency. We made tests about the linearity, which was the weakest point actually. But in the end, the conclusion of the paper is that it's good to go for current cosmology, for instance. So that is, we have stability in terms of photometry at the millimag level, even though it's not easy to get there, but you can get there. And so, and this is the previous generation of CMOS. The new generation is much better in terms of for instance, the noise distribution is more Gaussian. The tail is less important. We have better stability of the quantum efficiency. So my answer would be right now, I think if you work hard enough, it's not as easy as CCDs, but there are other advantages as you could see. And so I think, and once again, this is a cheap model. This is a model this is the camera with the CMOS is made by Sony. It's not one of these expensive Teledyne CMOS that cost 40,000, more maybe a piece. So I think we are there.
There is a question online.
Okay, go ahead.
Okay, hello, hi. My name is Łukasz Wyrzykowski, and this is very interesting topic, and I think we've met already in Paris at one of the microlensing meetings. This is very. I think this is the game changer for small telescopes, as Vasilis already mentioned, and we are running a 100 telescope network for time domain astronomy, and for these small telescopes located in sometimes good places, sometimes not so good. This would be a great way to improve their facilities. I'm just wondering, what is the optimal field of view? They don't have very big field of view, these instruments. Also, probably going to denser fields of the sky. This is actually where we are mostly interested in, is probably beneficial, but correct me if I'm wrong. The more stars you have, the brighter stars you have in your field of view, then the better your model can be. And also my question is, have you done any tests on kind of time domain photometry? How much does it improve? This is what interests me most.
No, yeah, sorry, there was some Larsen. No, we have so we had only, that was one limitation when we hit and we had COVID also, that didn't help, is to get these nice sequences. First of all, the main issue we had is to find a telescope that has a sufficiently good image quality. There are lots of telescopes around here, especially the small ones. They good excellent images, but down to 0.5 arc second. So basically down to the typical things, best thing, first things, thing you can get. But when you start playing this game, you see that actually they are not diffraction limited. So this is the main issue currently, is to, especially when, as you said, you have this network of telescopes that you don't necessarily have much control on. And it's really, this is a limitation currently, is that you need good image quality. And yeah, but on the other hand, I think I mean, seeing mitigation is only part of the story. There is all this issue of having a system online, a pipeline which can work with video data. So this is also where a lot of work has to be done. And I would say that atmospheric, the mitigation of atmospheric turbulence is the icing on the cake.
Last question, Kostas? No? So go ahead. Last question.
So I was wondering whether we can bypass the problem of having enough stars in field of view with lasers now. We don't need to mount many lasers, they just shoot at, you know.
Yeah, but you will use it a lot because, for instance, the isokinetic region for a high turbulence layer, like 10 kilometers or more, is something like 5 absolute or 6 absolute. So maybe a grid, you would have to project a grid on the sky.
But you can also shoot at very fast rate, you know, so you
Yeah. Whether then you're yeah.
Aside from that, I was wondering whether once you have the atmospheric turbulence model, not data, you can actually build a model on top of that.
Yes.
So you actually bypass the whole thing.
And there is another thing, is that if we go the way, you know, we generally think in the way of fast guiding. This is what people did before because they had nothing else at their disposal. If you're sampling sufficiently well your PSF, you not only have the centroid, but you have, if you have a speckle, a subspeckle, and so on, you get extra information of what goes on the turbulence within your pupil. So there is extra information there that I guess that here in what I showed, the network is able to use, which you might also use to get what, so as we said, you can get through a physical model of the turbulence and build on that and close the loop actually. I agree. So that's because we have more than just the position of stars at a given position. Makes sense. I'm saying. You see what I'm saying? So yeah. So but I say there is a playground here, which is I think interesting. So you don't need much astrophysics while you're doing that, but it's interesting, which is worth exploring. Maybe we'll be disappointed. As I saw, there have been efforts in the past which ended up, well, it was interesting, but it was too difficult. It's a difficult subject, but I think it's interesting. Lots of data, I mean, even more. For instance, with a small camera, 20 megapixels, we get the data rate of LSST, just to give you an example. Just with one of these emitter. So lots of data, but maybe interesting results.
Okay, so thanks, Emmanuel.